All right. And how was the homework? Easy?
Oh, absolutely.
Well, I was the purpose. You had to do a little bit of extra research, right? Well, I'm going to show you. I'm going to show you the string solution. So I suspect that most of you did the wall of if statements,
Yes.
right? Yeah, but I mean, I've said, right? Get it working first, then look to see if there's ways for you to clean it up a little bit, right? That's okay, but you spend time on it. Okay, you had a whole bunch of errors you tried to fix, and now you still have a whole bunch of errors left. Perfect. Perfect. Yeah, I mean, I want you to think about when you're working on your assignments, think about this kind of like one of those, like if you're playing an old Super Mario Brothers game or something, we're on a level that's kind of hard and you keep failing over and over and over again and dying, but you just stick with it. Finally, the moons align and you get through the level. It's like that. It really is. And eventually you become those one of the people online that does the speed runs. Yeah.
They got excited.
Yeah, they beat the game in 4.5 minutes or something like that. All right. So let's take a look at this. Remember they used to be the Guitar Hero ones.
That's how you get arthritis.
Yeah, and then there's guys who do a lot of Mike Tyson Punch Out still. That was one of my favorite games when I was younger. But then when Tyson went to prison, they re-released the game with a different end guy. Same same logic. Just looked different. All right. So let's look at so what did I say? Update decimal to base. Blah 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 to support all bases up to 36 and show the answers in the correct order. Okay, so we were doing two separate things here, right? On one hand, we're writing a single function that works for all bases, right? Okay. Shut up. Writing a single function that works for all bases. I think what we have now, it works for up to base 10, right? Then we start getting into the letter stuff, right? All right, so we need to write some code that works for that. All right. And you online folks, if you log into Zoom with your Concordia credentials, you won't get put into the waiting room. You'll just get put right into the class and it will save you time and me time. All right, so let's look at what we got here and see if I can figure this out. All right, so we don't need any of these guys anymore, right? Because we've written now our generic function, decimal to base. We have this function called number to letter. And this is the guy that is going to take in a number and spit out the appropriate letter based on it. So if we pass it a 10, it's going to give us an A. If it's going to pass an 11, it'll give us a B, so on and so forth. All right, so let's go down to that. So we have several if statements so far, right? So let's just do it the fun way first, right? So the expectation, if all of you sat down to do this, is that you'd start off by just making your wall of if statements, right? So we have F, G, H, I, J, K, L. Can any of you actually say the alphabet without singing it in your head? It's like a thing, right? It's kind of bothersome, I guess. All right, so didn't I put on caps lock? So writing all these if statements, not the end of the world, but does seem tedious, right? All right, then I got to go update my numbers. So this is 16, 17, 18, 19, 20. We really hope that that string solution helps us a lot here, right? 21, 22, 23, 24, 25, 26. Eight, 9, 30, 31, 32, 33, 34, and 35. Hence base 36, right? 0 to 35 was the legal things. Okay, so now I have my monster if wall of if statements here, and if I happen to pass it a number outside of that range, this is going to give me my question mark at the end. All right, so let's go down to our code down here. All right, and we no longer have these guys. We no longer have these guys. Now we just have this decimal to base dude, right? All right, so same logic as we had before. It's going to mod it by the base. Okay, except now we need to convert for any number greater than or equal to 10, we need to convert it to a letter. Otherwise, we'll just keep the number that we have. Okay, so the way we have it written right now, I can give it some giant number. Let me take my string stuff out here. And we'll try to get this. So let's go to 32. So there is 32 in, or that giant number in base 32, but we have to read it from bottom up. So that's PRAI1D. So far, so good. Okay. So first part of the assignment is get our answer shown all in one line, but in the right order. Right? Because right now it's printing it in reverse because we did not know how to build up an answer first. Now we introduce strings, so now we can build up an answer. All right, and I mentioned that you're going to start off with the empty string. So inside of decimal to base here, I'm going to go ahead and I'm going to say, call this guy answer. String answer, we'll start that off as the empty string. All right. Rather than outputting directly to the screen here, we want to take our answer from this and we want to tack it on to our answer. All right. So I'm gonna do this in 2 steps. I'm gonna first build it in the order we hit it, which will still be the wrong direction. All right. So I'm gonna say answer is equal to answer concatenated with, and we want to get this number to letter of temp. Oh. Ay. Sorry, I've been coding in Unity on a Windows machine last 2 days, so the copy and paste uses different keys. All right, there we go for that. So we'll just tack that onto that guy. We'll comment that out. So answer will equal answer concatenated with whatever number to letter returns, passing it this number. We're only passing it the number if it's greater than 10 or equal to 10. Similarly, down here, we're going to say answer is equal to whatever answer currently is, concatenated with, we want to say temp. But we saw from class last time that we don't actually, the concatenation operator, that plus sign, does not allow us to glue a string and a number together. We have to use a special function to do that. So we have a thing called toString, right? Where am I at here? So we're going to say toString. Is that how it is? Like that. So we're going to use this function called toString, which is built into the string library that I can pass a number to, and it will give me the string version of that number, which then allows me to tack it on to answer. All right. After this while loop is completely done, we'll do a cout answer. So what does this loop do? It goes through over and over and over again, just like before, whittling it down to 0. Each time through, it builds up our string answer. It adds something onto my string answer. All right. Nothing's been displayed yet. All it's doing is adding stuff. It's adding a character, a character, a character, a character. Then as soon as we're done building that guy up, then we print it once. Make sense? All right. So if I run this guy again, there is our answer as a single string, but it's still in the wrong order. Okay. So what do we do with this? Well, nothing says that we had to have answer at the beginning of this. So there's our answer in the correct order. So each time through, what I did is I concatenated the next character onto the front of my building up answer. Make sense? Now, you could have done a whole different thing. So let's stop here for a second. So I decided to build it in reverse as I was going. Not a big deal, but making this little switch here, even though you see it now, wasn't difficult, but maybe it wasn't something that jumped out at you when you were writing this, right? So maybe when you were writing this code, you left it in its old state. So what you had in the end was your answer in reverse. Okay, so you almost have the right answer at that point. So maybe you decide, okay, well, I'm going to run back out to Home Depot. I'm going to buy another tool that I can throw a string at, and it gives me that string backwards. Right? So I can go up here and let's just invent another tool. So we're going to write another function. Now, the reality is there might be something built into the language, right? But we haven't been introduced to it. It's not a big deal here. We're just going to write it ourselves. And might as well make it homemade. So I'm going to write something that returns a string. We're going to call this guy reverse string. It's going to take a string as a parameter. And I'll go and, well, I can invent it anywhere down here. So I'll just invent it right here. All right. So I want to walk through this string from beginning to end. And, or I'm sorry, from end to beginning and build up another string. Well, I'm going to need a couple of pieces of information in order to accomplish this. I need to know what the length of a string is, right? I think last time I at least had it up on the screen.
Nothing on my.
Getting left nothing in my output.
Okay, well, then you're not quite doing it the same way I'm doing it yet. All right, so I probably had this pop up last time, at least for a minute or something like that. We have a whole bunch of different functions here that work on this guy. We've seen a couple of them. We've seen the toString and that kind of stuff. So there's this one guy here. One's called size, one's called length, that returns the length of a string. So we can ask a string to report its length. Well, let's go and look at that. So I'll just do it out here in main just for testing purposes. So I'll say string s is equal to hello. Cout s. And that's going to print out hello to the screen, right? So there's my hello to the screen. Now I'm going to do cout s.length. I am asking that string object. So we're dealing with an object-oriented language here. All right. Up to this point, with the exception of the very end of last class, we've been using primitive types, things like ints and chars and booleans, those kinds of things. Primitive types, all they can do is hold a value. That's it. And that's all we've been using them for, right? You want to store the number 7? Throw it in an int. All right. Well, now we have something that's a little bit more powerful. That is a string. For starters, it allowed us to store a collection of things, in this case, a collection of characters. But strings not only can hold stuff, they can potentially do more. So in this case, one of the things a string knows how to do is it knows how to report its length. I can say string s, call your length method, telling me how many characters live inside of that string. And just to show you the difference here, I'm going to say string s2 is equal to elephant. And we're going to call the exact same function, but this time we're calling it on a different string. We're asking S2 to tell us what its length is. All right, which is going to be different than the length of hello. In this case, I purposely picked the longer words. This is going to give us an 8. So we'll run this and we see a 5 and then we see an 8. So we now have this additional tool, length, that can tell us how many characters currently exist in a string. All right, now that's going to be helpful for us because we are going to need to start at the end of the string and walk towards the beginning of the string and build up a new string, which is that string in reverse. Okay, so let's start off by exploring a couple of things here. Now we know how to get the length of a string. How do we get a certain character from a string? All right. So if I want to get this P from the string elephant, how do I get that guy? Go to all right. So strings are zero-based implementations of arrays, which can only hold chars. Okay, so obviously it makes perfect sense now, except what's an array. All right, I'll give you a hint. We're getting to arrays here relatively shortly. Arrays are like strings, but they can hold things other than chars. You can have a collection of integers, a collection of chars, a collection of booleans, a collection of yada, yada, yada. Okay, anything we want to have collections of, an array lets us do it. But right now we're working with just characters because we want to have this flexibility of building things up, and strings have a lot of things built into it for letting us do that. So when I say zero based, I'm going to show you what that ultimately means. We're going to draw a picture of our string hello. So when I say something like string S is equal to hello, what that actually does is it produces something in your computer's memory that looks like this. I wish you could just turn off its suggestions that like, hey, do you want this capitalized? I probably would have capitalized it if I did. So it builds something that kind of looks like that. This is a collection of individual chars that all live next to each other in memory. Okay. Now I'm going to put a thing below this. Like that. So I mentioned that strings are zero-based implementations of arrays, which means that the first element in our string is at position 0 in that string. All right, so in this particular example, the length of S is 5, but the legal positions are 0 through 4. That makes sense? A little bit bigger here. All right. So now if I have a string S and I want to get at the second L here, the second L is at position 3. I would say S, open square bracket, 3, close square bracket. That says, go into this string named S, grab for me the character that lives at position 3, which is that guy right there. If I change that 3 to a 4, it's now going to grab that guy. If I change that 4 to a 5, it's not going to be happy. But it's going to be far happier in C++ than it would have been in a newer language like Java. Now, I don't necessarily expect any of you to necessarily know the answer to this, but how many of you have heard of this? But how many of you ever heard of an error, like when you're looking at movies with hackers or something like that, of a buffer overflow error? So a buffer is something that looks like this, a collection of stuff. This is an example of a buffer that's built for holding 5 things. A buffer overflow would be that you walked off the end of it. Okay. Now, the reason why that could become a problem inside of computers is I'm going to add a third row here. And I'm going to make up memory addresses so they're easy for us to see. So we hit the lottery and we had memory addresses that are very easy to read for us instead of scary hexadecimal values. All right. So I'm going to go ahead. I'm going to steal one of these guys here. This is my variable S. And S actually holds the value 100. So my string S here, so this is just a variable like any other variable. Here's the type, here's the variable name, here's the value. S actually holds a number. This kind of goes back to our discussions about primitive types. That is, with primitive types, we have, remember, bytes, shorts, ints, longs, they all hold whole numbers, right? Fine. But then we saw chars. Well, chars are characters. Human beings like characters, but we saw that computers actually store those guys as numbers. And then we have that lookup table, the ASCII lookup table that allows us to take that number and find the char equivalent. All right. So again, computers like storing numbers. So here's another example here. I've created a variable named S. What's actually getting stored inside of S is this memory address 100. So I'll put a little comment here. S actually holds the memory address where the beginning of the string is stored. All right, when we create a variable, a place in memory is built for that variable. Okay? That's a memory address. And then as you put a value in there, it gets put into that place in memory. Now, strings being things that hold multiple values. Up to this point, we just said like int a equals 5. That would create one little place in memory. We would put a 5 there, and this variable knows that it's pointing to that guy up in memory. But now I have something that holds a whole bunch of characters. Now, the only way strings work, and the way we're working with them here, the only way it functions is if we keep track of where the beginning of that string is. So that if I want to get the first character, I go here. The next character, I take a step to the right, a step to the right, a step to the right. I'm walking through memory one little step at a time. So let me stretch this back out. So I could probably do it better than that. Okay. So strings are stored in what is called contiguous memory. Fancy way of saying memory that is right next to each other. So what I've shown here is I've shown from a human being perspective, these are the chars that we're holding, HELLO. That's pretty comfortable for us. Those are the values we wanted to store inside this string, right? Then I'm telling you that there is a mechanism built into C++ for accessing individual elements of a string. So to get the H, we ask for the element at position 0. The E is the element at position 1. The L, position 2, the other L, position 3, the O, position 4. Okay? And we also know we have the facility to ask how long is this string? How many characters are in this string? So for this guy, it's going to give us a 5. From a human being perspective, we don't really care where the computer ultimately puts that, right? This kind of goes back to what I've been talking about since the beginning, where as computer scientists, it's important for us to understand and appreciate what's happening behind the scenes. But in practice, when you're out there working in industry, you really don't care what memory address it put your string at in your computer, right? As long as it put it somewhere and you can access it, you're cool with that, right? All right, but for us to learn about this, we want to understand how strings function, because they give us some information about how a lot of things inside of computers work. So S actually holds the memory address where the beginning of the string is stored. This is often called the base address. Often called the base address. Base address is the memory address where something starts. technically all things in memory would have a base address, like integers would have a base address, but the base address is also the full address of where that value is stored. Because if I hold a number, it's only getting stored in one place in memory, right? It's a big enough little chunk to hold the size of the value I'm holding, but it's only getting stored in one memory location, let's say. But strings, we're asking it to store a collection of things. In this case, 5 individual chars I want to store in memory, but I want to associate all 5 of those guys with a single variable name rather than 5 separate variable names. Make sense? Because if we had to have multiple variable names to store all the characters in a string, we're going to be very limited on how we work with strings, because if we're going to work with hello, we need to have 5 variables. You're going to work with elephant, you need 8 variables. That's going to be very difficult to do at runtime when we don't necessarily know how much we're going to build up this string. Think about our program here. We have a while loop that goes through and it just keeps whittling down a value towards 0. Tacking something onto our string, right? So before we run our program, we don't necessarily know how long our string is going to be. Depending on the value we give it, our string might be 1 character long. It might be 200 characters long. That makes sense? So strings have the ability to dynamically change in size. I referenced up top here that strings are implementations of arrays. So a lot of the stuff I'm talking about here really directly relates to arrays, except arrays don't limit us to storing just characters. But arrays also don't come with some of the quality of life functions that allow us to conveniently work with strings. Words, human beings use words a lot, right? So being able to store things as strings that have some extra functions that allow us to conveniently work with them, it kind of makes sense for that to be in a programming language. Or if I just want to store a collection of 1,000 numbers, I just need a place to put them, and I'll siphon through them later on, sift through them later on to maybe find the biggest value or something like that. All right. So really, strings are a special implementation of arrays. They only hold characters, and because we have that constraint, we have some other things that they can do that make our lives easier as a programmer. But behind the scenes, strings are stored inside the computer in the identical way as arrays are stored inside the computer. That is, we keep track of where does our collection of stuff start in memory. What's the base address of that? All right, in our line of code here, string s equals hello, nowhere in there did we give it that memory address 100, right? When we asked our computer, we told C++, I want to create a variable named s, and I want it to be a string. C++ went out and did some negotiating with the operating system. Think of it like there's a real estate agent inside of the operating system that goes and finds you a nice plot of land in memory, somewhere to store that string. Now, realistically, in C++, there's probably some sort of maximum length of a string. My guess is it's probably either length of short or the length of a int. So maybe you can have 2.1 billion characters in a string as a maximum number. All right. So it's going to go ahead and get you a plot of land big enough to hold, more than likely, the actual implementation probably says, I'm going to get you enough land to maybe hold your first 30 characters. If you start wanting more than that, I'm going to have to move some things around. We'll lift your house up. We'll take it to a new, bigger plot of land so we can add some more stuff onto it. All right. So behind the scenes, it's pretty inefficient. But from our perspective, we don't care. We really don't care where in memory it actually lives. But we want to, in this course, we want to understand what's actually happening. All right. So when we define that variable, we say, C++, I want to create a variable named s. I want it to be a string. And C++ is going to talk to the operating system and go and find the perfect place in memory to store that thing. And in my example here, I decided it found this nice friendly memory address number of 100. All right. You can think of, I think I said this maybe the first week of class or something, where we were talking about, actually it might have been the second week, we were talking about hexadecimal values. One of the ways hexadecimal values are used is for memory addresses inside of a computer. All right, because our computers today have a lot of memory, right? 4 gigabytes, 8 gigabytes, 16 gigabytes, 32 gigabytes, 64 gigabytes. You know, that's probably kind of hitting the top of what a average good computer has. Maybe 32 gigabytes is kind of what's considered a high-end computer today. You can get servers with 2 terabytes of memory. You can, you know, some of you might have gaming machines that have 64 or 128 gigabytes of memory. But at that point, it starts getting kind of crazy how much memory you have. But every single time our demand for our software gets bigger, we need more memory, right? I think I mentioned the Bill Gates famous quote, "You'll never need more than 32K of memory." Or, you know, 32K can't hold very much, right? In fact, 32K is the size of an int, right? That's not that much. That's not that much. All right, in terms of individual things that can store. So when we built this string, C++ went out, talked to the operating system. The operating system said, "Hey, I have the perfect plot of land for you. You can find it at address 100. Memory addresses work just like real life addresses work, except they're even easier. They just look scarier, right? Because they got those hexadecimal values, and that freaks us out because it has all the letters in it and stuff like that, right? So in a computer, all things live on one really, 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 really long street. You know, when you have your home address, you have 1, 2, 3 Adams Street, and you have a city, a state, a zip code. You have all these individual pieces that further describe the address of your house, right? Because there could be an Adams Street in 500 towns, right? So we need to be very specific about where your particular house lives. So our addresses in real life, human versions of house addresses, are pretty complex relative to computer addresses. Yet we've been using them our whole lives so they don't intimidate us. Make sense? Computer addresses we haven't been using our whole lives, and they're represented using hexadecimal values because the numbers get really big, which is why I purposely chose effectively decimal values here that are more friendly for us. All right, but what we have here is we have our string at house number 100. All right, so down this street at the 100th plot of land, there is some land marked off that can hold a house big enough to hold 5 characters. Now in C++, the size of a char is a single byte. In newer languages like Java and C#, the size of a char is 2 bytes. Remember we talked about ASCII versus Unicode? Finally, somebody decided, hey, there's other languages in the world other than English. So we can, with Unicode, we use 16 bits to represent our chars. That way we can have up to 65,536 unique characters that we represent, not just 256 characters for the English alphabet, plus our numbers, plus our punctuation, and then we had a whole bunch of smiley faces and crap like that to fill in the blanks. All right. So whether you're using an older language like C or C++ that only has a char of size 8 bits or 1 byte, or you're using a newer language that has a size of char that's 2 bytes or 16 bits. In C++, our first character would be at memory address 100 in my example. And then we take a 1 byte step to memory address 101, where I'll find my second char. Then I take a 1 byte step to memory address 102, where I'll find my next char. All right. So if you want to think about this in terms of a real life plot of land, let's say you're building a house, you're building a farm. Let's say you're building a farm. And this is 5 acres of land. Okay. So on the first acre, you're going to build some stuff or plant corn or whatever. And the next acre, you're going to do something else. Next acre, you're going to do something else. So we own this land that is all 5 of these acres. So at house number 100 on the road, that's where our mailbox is. But the actual land extends past that some until you get to the next mailbox, right? because that land, not all plots of land are the same, right? Your house might be on a half-acre lot. Their neighbor's house might be on 3/4 of an acre lot, and the farmer down the street might be on a 20-acre lot, right? With all sorts of farmland and things like that. So this is just like real life memory addresses where the things at an address are of different sizes, right? So same thing's going on here. A char is 1 byte big. So if the first char lives at memory address 100, the next char would live at memory address 101. The next one would live at memory address 102, 103, 104. Make sense? All right. So now I'm going to show you the math that makes this first line true, because everything in computers is ultimately backed up by math. They didn't just arbitrarily say that, oh, well, we're just going to say that H lives at bucket 0 instead of at bucket 1. As a human being, we might say, well, H is the first character in the string. Yet in a computer, it's actually the 0th character in the string, sort of. Make sense? Okay. Computers didn't just decide, these languages didn't just decide to make it a 0. It mathematically is a 0, and I'll show you why. Let me move some stuff around here. Give myself some room for my pictures. Now I'm going to draw a little line here, and we're going to name it something. All right. Oh, one thing I'll mention, I haven't made a decision yet, but I'm debating actually starting to use, I mentioned that we'll start switching over to like Java, different programming languages as we go through. I might actually introduce the game programming stuff in this course. So I think based on some of the struggles some of you are having, you might benefit from visually seeing things move around rather than having all this text-based stuff. So I might do that jump here sometime after the midterm. If things won't look pretty, you'll put like a box on the screen, right? And then if you move the box 5 things to the right, the box is now here, but you'll see the box move. Okay, so let me think about that some, but I am debating that. So we'll technically then be using C# instead of Java, but we talked earlier in the course, they're the same language. There was a lawsuit that made them different. All right, but I'm going to draw this little arrow here. The reason I drew that arrow is this guy has a historic name that freaks programmers out. This guy's called a pointer. Why? Because it points to a place in memory. My variable S holds a number. That number points to a place in memory where my value actually lives. Make sense? Doesn't seem to be an overly difficult concept, right? Until you print out the value of a pointer. Pointers hold memory addresses. So if you print out the value of a pointer, it's a scary looking hexadecimal value, and beginning programmers flip out. Unfortunately, even advanced programmers flip out. And this is why I spend so much time talking about what's under the hood. Because understanding this stuff empowers you to solve problems that, frankly, a majority of people in industry can't solve because they don't actually understand how computer memory works, when computer memory actually is easier than real life addresses. We just never actually jump into the pool and look what's under the hood. So that's why I kind of force us to do that. All right, so this variable S holds a number, which is the memory address where my string lives in memory. So what S actually holds is the base address of my string, which is said to point to where my string lives in memory. Okay, we'll talk more about that when I introduce pointers starting next week. All right, so let me show you a couple of things here. Why 0 is mathematically defended. So S at bucket 0 that guy is the character H, right? S at bucket 1, that guy is the character E. S at bucket 4, that guy is the character O. All right, everybody's good at that? Good with what I have there? So that kind of matches up to my picture here. Okay, now I want to emphasize something here. When you're using strings in your programs, 99.9% of the time, you don't need to worry about the red boxes. It's a truth. It's happening behind the scenes. But as the programmer who's using the string as a tool, you don't actually care where it got stored. We're understanding how it gets stored here, which is why we're revealing that information. Make sense? Sometimes you will solve problems where memory addresses are important. Most of the time, though, those values are not going to be something that you will ever see or care about unless you go out of your way to print it out. All right. But it helps me reveal how these things actually work. So bucket 0 is memory address 100. Why? Here's the math problem that supports that. So S at position I. Did it put an uppercase I? There we go. Is equal to the base address plus I times the size of the type. Are you, I'm definitely regretting using I. All right. So obviously crystal clear now, right? All right. So what does this ultimately mean in terms of numbers? Just like most things in technology, it actually means something easy. It just purposely looks cryptic so you can make more money, right? Makes you seem smarter. Okay. Now we already talked about base address, right? So the base address of our string here is 100. That's where it starts. That's where that plot of land where our string lives in our example here starts. That's the base address of it. That make sense? Any questions about base address? All right. That's not something we make up. It's something that's given to us when C++ asks for some memory to store something. All right. It gets the base address, which is that's the actual thing that gets stored inside of our variable, which is said to point to the thing inside of real memory. All right. So in this case, our base address is 100. Plus the current value of I. So in this case, I is a 0, right? In this case, I is a 1, I is a 4, because I'm showing an example of S at position I. So for all of these, the base address is 100. Followed by another math problem. That is the current value of I, so that one's 0. This one's 1. This one's 4. So far, so good. We're just filling in the variables with their current values for this particular example. So 100 plus 0 times the size of our type. Now, strings hold a collection of what? What kinds of animals live inside of a string? Bunch of chars, bunch of characters. And how big are characters inside of C++? They're 1 byte because they use ASCII in C++. Actually, in C++, we can do something like this. You can see out size of char. Let's make sure it's actually still using ASCII and not Unicode. Yeah, it's 1 byte. That's the size of a char, is 1 byte. So technically, you don't even need to know what the size of a char is. The size of a char is however big a char is. We have a function built into C++ called size of. You can throw it a type and it will tell you how big that guy is. If I change that guy to an int, we're expecting this to be a 32. 4 bytes, 32, 4 bytes, right? 4 times 8 is 32. If I make this a long, now it's going to be 8 bytes, 64. Here's my 8. Make sense? So that matches up to my slide where I had all the different ranges of values for bytes and shorts and ints and longs, and how many, a byte is an 8-bit value, a short is a 16-bit value, an int is a 32-bit value, a long is a 64-bit value, a char is an 8-bit value, which we saw here when we said, what's the size of a char? Said it's 1 byte, which is 8 bits. Make sense? All right, so back here, the size of our type here is 1, right? Because the size of a char is 1 byte. So we'll put 1, and this is the times. This is the times. This is the times. So there's our math problem. So 100 plus 0 times 1, order of operations, we do the multiplication first. What's 0 times 1? 0. 0 times anything is 0, right? So that's 0. 100 plus 0 is what? 100? What do we find at memory address 100? H, which is that bucket 0. Here's our next one. What's 1 times 1? Super hard math, I know. It's 1, right? So what's 100 plus 1? 101. There's 101. There's our E. That's at bucket 1. What's 4 times 1? 4. 100 plus 4 is 104. Here's 104. That's our O at bucket 4. The math has dictated why we have 0 indexing. This character here is at bucket 0 in my string because that is where it lives in memory relative to the base address. Bucket 4 is how we index this character right here because that is where it lives in memory relative to the base address. It is an offset of 4. We go to the base address first, then we take 4 bite-sized steps through memory to get to our character. Make sense? When we talk about arrays, it's going to be this, or talk about arrays of integers, it'll be the same thing. Just instead of taking byte-sized steps, char-sized steps, we'll be taking int-sized steps, which are 4 bytes. We take a bigger step because each int will take up 4 bytes of memory to store, where each char only takes up 1 byte of memory. So instead of a shoebox, we now have, I don't know, one of those bigger Tupperware things to store our ints. So we have to take larger steps through memory to get to our next int, our next int, our next int. That makes some sense? All right, so this is what's happening behind the scenes in strings. Now, again, we're not going to be interacting with this stuff most of the time when we're using strings. But understanding how strings actually work allows us to pick the right tool for the job when you start solving harder and harder and harder problems. And what I mean by that is, even though we've mentioned that our computers today have tons of memory, so, we don't have to worry about memory anymore. We don't have to put some things in bytes and some things in shorts. We'll just put it all in an int. Even if I'm storing the number 5, an int is overkill, but who cares? And if an int ends up not being big enough, we'll just put it in a long and hope for the best, right? We don't really worry about wasting too much space because we have tons of memory in our computers today. But our computers don't have an infinite amount of memory in them, right? Which means that you may run into some problems, especially when you start getting into some of the artificial intelligence stuff, which uses huge amounts of memory to solve its problem, where you do need to start worrying about running out of memory, okay? So what does that mean? That means that understanding how things are actually working under the hood might dictate which programming tool you use. So for example, the third programming class, CSC200, is called data structures. All right. And in that class, you learn about linked, linear and nonlinear linked data structures, which is a fancy way. A linear linked data structure is effectively an array. But instead of the things being contiguous right next to each other in memory, they could be strewn all about in memory, where one thing links to the next thing, which links to the next thing. They don't need to be right next to each other. Why is that important? Well, here's the real life example. Let's say you've built a gigantic house on your half acre of land. So your house goes right up to the edges, right? And now you want to build an addition. You can't, because your addition to your house is going to spill over into the neighbor's yard, and he's probably not going to be happy. But you really want to build that addition. What do you got to do? Got to move. You either, you usually would just sell your house, buy a new house, and put the addition on that one, or buy one that already has that extra room. But in the computer world, we can, defy gravity, and we can pick our house up and go and take it someplace else, right? So we can say, well, my house used to be on a half acre of land. So what I'm going to do is I'm going to go ahead and I'm going to find 3/4 of an acre of land. And I'm going to copy my house over there. And then I'm going to destroy this one. Wasted memory. I'll give it back to the operating system. You can have somebody else can use that now, because I've already copied my house over to this new plot of land that I acquired. Okay. And now you have a little bit extra space to build your addition. Now in real life, even if we decided you were super strong and had the ability to duplicate a house at the snap of a finger, and you had all the money to buy the second plot of land, is that a very efficient way of adding an addition? Duplicating your house, burning down the original one, then adding the extra stuff onto it. Week later, you decide I want a sunroom now. Well, got to do it again. Move it to a new plot of land. That's how arrays actually work. So if you build an array capable of holding 10 elements, and all of a sudden you want to put 11 elements in there, you got to move it to a bigger plot of land so it can hold the 11th. Then if you decide you want to put a 12th element, you got to move it again to a little bit bigger plot of land to put your 12th element. Linear data structures allow you to say, well, we're going to trade off a little bit of performance because computers are really fast. And instead, we're not going to require things being right next to each other in memory. We're no longer going to adhere to this math problem. We can't necessarily assume that this I is 2 char size steps off of the base address, because it might not be in contiguous memory. In which case, this guy, in order to get to the I, you would start here. And this guy would hold an additional piece of information. Not only does he know about himself, he also knows the memory address of the next guy. So I would follow this through memory to get to the E. Then he would know about the next guy after him. I'd follow that through memory to get to the L, so on and so forth. So if I want to add an addition, the real life version of this is, you want to add a sunroom? No problem. I'll just buy a little land over, 3 blocks over, and I'll put my sunroom there. So whenever I want to use the sunroom, I go for a short hike, right? Computers, you can, let's say, teleport, right? You just jump to that memory address and everything's good. All right. Where in real life, we probably wouldn't do that, but computers let us do that. So, not always is it identical to real life, because we can pull things off in computers that you would never do in real life. But the thought process is the same. In real life, we would say building my sunroom 2 blocks away is not acceptable. Even if I bought land, which we could do, and we could build a sunroom 2 blocks away, we would just say that that is not a good solution to the problem, even though I still have my house and now I have a sunroom. The proximity of those two things is just not going to make a human being very happy. Make sense? All right. So in computers, we can say, oh, well, that's not a big deal. If I want to go 2 blocks over, I'll just teleport over there. I'm 2 blocks away. New memory location. Now I'm in my sunroom. All right. Acceptable solution in computers, not acceptable solution in real life, but a possible solution in real life. Okay. But this is how math works behind the scenes inside of our strings. Now, I'm never going to ask you specifically about this on like an exam, but it's important that you know the information, because sometimes having this knowledge of how these things are stored behind the scenes might give you the information you need as to what's the right tool for the job when you're about to do something. And let's say you're doing something with AI that's using tons and tons and tons of memory. Building a gigantic array, collection of chars in terms of a string, a collection of integers, whatever, just a gigantic array may not be very efficient. Because even though your computer might have 16 gigabytes of memory in it, presumably you already have stuff. So here, what is I think I have it at the top. My computer currently has 57.84 gigabytes of free memory. Okay, I think my machine has 96 gigabytes of base memory, a lot of memory in it. That means that I'm already using 39 gigs of RAM, right? Now, chances are that RAM isn't right next to each other. I got, a house built here and a house built here and things strewn all over those 39 gigs of memory, right? So let's say I need to store something that is 57.8 gigabytes big. Technically, I have the memory for it, right? I just have the memory for it. But I may not have enough contiguous memory to store that many things. Maybe the biggest plot of land I can find in a row is 4 gigabytes without something else sitting there, right? This is a real life example. You run into it when like Meyer went into Grafton. Meyer took a long time to go into Grafton because there were houses and stuff built along there. And they bought up a bunch of land, but if you've driven by there, there's this one little house on the south side of Meyer that refuses to sell. So that's why they aren't building more stuff out that way, because they can buy the land after that house. They got the land before that house, but the land at that house, they're not willing to sell, holding out for more cash, I assume. Why not, right? let Meyer pay him more cash. But these examples exist in real life. Chances are I don't have 57 gigabytes of memory in a row in my computer, even though I technically have enough space available to store that much data. Therefore, if I need to store that much data, I need to then pick a different solution, a solution that allows me to store some of the stuff here and some of the stuff here and some of the stuff over here, put it in the little nooks and crannies, right? To really, take advantage of all my space. One's not necessarily better or worse than the other. It's just what's the right tool for the job. All right, makes some sense? All right. But out of all this mathy stuff, whatever, what we really got out of this lesson, besides understanding how strings work behind the scenes, is we now know two things strings can do. We know that strings can tell us how long they are, and we know that strings allow us to access individual elements of them. And now we also know how it accomplishes those things, right? The length, what does it do? Starts at the base address and keeps walking until it walks off the end. Susie, as soon as it falls off the cliff, he stops counting. That's how many characters I found in this case. Okay, I found 1, now 2, now 3, now 4, now 5, now, because he's falling off the. That's how it figured out the length. All right. The reality is the way strings are stored in C++ is there is a terminating character, a \0. And that marks the end of the string. So really length would be a loop that starts at the base address and keeps walking, counting by 1 each time until it finally runs into a \0. That's how it actually works behind the scenes, rather than the jump off the cliff thing. Which means that every string technically takes up 1 additional character of memory than you're actually storing. Okay. Also won't test you on that, but that's something that is in existence behind the scenes. But now we have two more tools available to us. What's the length of a string and how do I access an individual bucket? So we go back in here and we want to write this thing called reverse string. Reverse string is going to take a string in as a parameter. So for example, S might equal hello. And I want this guy to ultimately output O-L-L-E-H, hello in reverse. Now, this is only for the example where S is equal to this guy. If S came in as elephant, it would output elephant in reverse, so on and so forth. So I'm going to have a string. We'll call it answer again. Then I'm going to use to build up my answer. I want to write a loop that walks from the end of my string to the beginning of my string. Remember when we did our countdown and then our countdown in reverse? Same loop. For int I is equal to the last legal bucket in a string. So hello has 5 characters in it. So hello's length is 5. But the last legal position in hello is what? 4. S dot length. So if I ask how many characters are in S, some of you maybe would have said, well, isn't there 5? I just gave you a sample example here. How many characters are in S? S dot length number of characters. Because this is a function. People can call this function with different inputs. They're going to pass me some string. I can find out how many characters are in that string by asking the string, what's your length? All right, so I'll start I off at S dot length minus 1. I'm going to keep going as long as I is greater than or equal to, what's the first legal position in a string? 0. So I'll keep going as long as I is greater than or equal to 0. And each time through, I'm going to subtract 1 from I. So it's going to go from 4 to 3 to 2 to 1 to 0. Now, all that loop does is it takes I on this voyage. In my example here, from 4 down to 0. I have to now choose to use that value I to access the character at a particular place in my string. So I might say answer is equal to S at position I. Concatenated with whatever answer used to be. So the first time through, S set bucket 4 will be the O, and I'm tacking it onto what answer currently is, which is the empty string. So now I have the string that is an O. We'll even prove it here. So we'll just do a little C out. We'll get the current version of answer. So look under the hood a little bit, right? So every single time I'm tacking something on, we'll just show you the current value of answer as it's building up. All right, then it's going to loop back through. Now we're looking at the L. We'll tack the L onto what answer currently is, which is just the string O, so on and so forth. All right, now this is going to rebuild it in the same order. If I want to build it in reverse, I have to take whatever answer currently is and add on to it the character I just ran into, because I'm walking my string from end to the beginning. Now, when all is said and done here, since I've said I'm going to return a string, I'm going to go ahead and I'm going to say return whatever my answer is. So if you want to test this, we'll go ahead and see out whatever reverse string returns for the string hello. My final answer, what this guy right here boils down to, should be hello in reverse. But before I get that final hello in reverse, I'm going to see all the loops through as it builds up hello in reverse. So there's that O, OL, OLL, OLLE. And then here's my final time through that loop. And then here's when I actually received my answer outside of the function back in main and printed that out. See how that's working? So now that we've seen that, how it's building it up, I could choose to take that little line out there. So now I will only see that final answer, my string in reverse. So now what I can do down here is if I didn't want to build it in reverse here, so like what I have right here is my answer still backwards, I can call reverse string on my answer, and that will give it to me in reverse. So if I didn't want to build it in the right order, which we saw we could do at the very beginning, I could build it backwards, like we were already kind of doing. And then I can just call this one function to reverse what I just built in backwards. So now we should see our answer in the right order. All right. Now in our last 2 minutes, the string trick. All right, so number 2 letter. I'll write a second version of this guy. Call this guy number to letter string trick. So I'm going to say string map is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Now I know I hate. All right, so that's the whole alphabet, right? What position is this number 0 in? 0. What position is A in? 10. What position is F in? 15, right? There you go. And now you don't even need to ask the question down here, whether it's greater than 10 or not. You can just say answer is equal to number to letter trick of temp concatenated with answer. I'll comment out all this extra stuff here. And I no longer need to reverse it because it'll be built in reverse. So I'm building up answer in reverse. And there's my final answer. So you can either have all those if statements or take advantage of the fact that math supports how our bases work. A 10 is an A, an 11 is a B, a 12 is a C, so on and so forth, and all the way to the end of the alphabet. 35 is a Z. So all I need to do, if I'm given the decimal number and I want to get the character version of that, I just have to say string, give me the char that lives at this bucket. If I passed it a 0, it would give me a 0. If I passed it a 7, it would give me the character 7. If I passed it an 11, it would give me the character B. Make some sense? All right. So I'll save this. I will put the code up on Slack. I will have the exam up either later tonight or first thing tomorrow morning. Remember, you have until before class starts on Tuesday to submit that. So you can do it whenever you want. You just need to do it all in a single sitting. Okay? So that's your homework over the weekend. I'm not giving you anything else.
We get one or two.
No, one or two, who, what?
We get one or two.
Attempts, you get one attempt. One attempt at the exam. Technically, you can get your second attempt on the final exam to fix your midterm.
We got, at least get like a very. Bare minimum. Yeah. Unless we find a way to like just not.